Hello students, welcome to SuperProfs. The course which we are studying is Digital Electronics and this is lecture 5 on Boolean algebra and reduction techniques. Till now we have studied about the number systems as well as the logic gates. So in logic gates, after making or constructing a logic gate, we get a final expression which is known as a Boolean expression, but it is something somewhat large. So in this session, we are going to simplify these Boolean expressions and we use some reduction techniques. So to start with, first we are going to understand what are the number of distinct Boolean expressions for any n input system. So by using a truth table we can understand this. First of all, we should write a note which is for n input system. Okay, if there are n inputs in a system, then the number of distinct Boolean functions is equals to 2 raised to power n. Okay, this is a general expression. So here we can see that there are two inputs, that is x and y. So for two input system, the number of distinct Boolean functions we are getting is 2 raised to power 4, that is 16. So here we can see that there are 16 functions from f0 to f15, and we are going to see that all the functions are distinct in nature that can be made using the two input combinations. So first we complete this truth table. We have 0, 0, 0, 1, 1, 0 and 1, 1 as the input combinations. So to write all the possible functions, what we are doing, we were first writing 8 times 0. This is 8 times 0, 8 times 1. Okay, now 4 times 0, 4 times 1, 4 times 0, 4 times 1. Okay, now 2 times 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Now 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So these are the all possible combinations by a two input combination and all the possible distinct Boolean functions. So let us first see what is f0. So here we can see that for f0 all the output are 0 for all the input combinations. So we can write f0, or the final expression for f0 would be 0, that is null operation. This is known as our null operation. Now we are writing for f1. What should be f1? We can see that f1 is 1, or the output is 1 for only one input combination, that is 1, 1. So what is the function resembling to? Students, it is resembling to an AND operation, which is x dot y, which is equals to AND operation, because for AND operation the truth table is very similar with the function f1, because it is high, or it is high logic level when the inputs are high, unless it would be low. Okay, now we are going to see for f2 function. For f2 function, the output is 1 for the input combination 1, 0. So what would be the final expression for f2? It would be x dot y bar. It is known as inhibition operation. Okay, what do you mean by inhibition operation? It means x but not y. X but not y. Okay, this is f2 function. Now we are going to discuss f3 function. For f3 function, we can see that the column of f3 0, 0, 1, 1 is equals to the column of input x, which is 0, 0, 1, 1. So the final expression for the function f3 would be x, that is buffer gate. Okay, this is our F3 function or the output of F3 function. And now we are going to see for F4 function. F4 function, we can see that it is the output is 1 for the input 0 1. Okay, for all the other inputs the output is 0. So we can write F4 would be equals to x bar dot y. It is also an inhibition operation. Okay, this is also an inhibition operation. Now we are going to discuss about this is F4. Now we are going to discuss about F5. So we can see F5 is equals to the Y input, because F5 is also 0 1 0 1 and Y is also 0 1 0 1. So the final expression for F5 would be equals to Y, and it is also a buffer gate, because for buffer gate the output is equals to the input. Okay. Now we are going to see for F6. For F6 we can see that the output is 1 for two combinations, that is 0 1 and 1 0. So to write its final expression we are getting the expression for XOR gate, because for XOR gate the truth table is similar to this F6 function. So F6 function is equals to X XOR Y, which is XOR function. Okay, now we are going to see F7. What is F7? For F7 we can see that the input X and 0 for F7 the output is 0 for the input combination 0 0, and for 0 1 1 0 and 1 1 the output is 1. So this is the truth table for OR gate. So F7 is an OR function or OR gate of X and Y. Okay, now we are going to discuss F8. So for F8 we can make a relation between F7 and F8, that F7 and F8 are complement to each other. That is here 0, this is 1, this is 1, this is 0, this is 1, this is 0, this is 1, this is 0. So we can write what is the complement of OR gate, students? It is a NOR gate. So for F8 it would be X plus Y bar, which is our NOR gate. Okay, this is F8. Now we are going to discuss about F9. What is F9 function? So we can see that this function and our this function is 1 0 0 1. Okay, this function is just the complement of our XOR function, that is F6. So if we want to make a relation between F6 and F9, we can see it is just complement to each other. And what is the complement of XOR? It is an XNOR function. So it is X XNOR Y, which is equals to XNOR function. Okay, this is an XNOR operation. Now we are going to see for F10. So for F10 we can see that F10 column and Y column are just opposite or complement to each other, because F10 is Y is 0 1 1 0 1 0 1, and for F10 it is 1 0 1 0. So the output expression for F10 would be Y bar, which is known as NOT operation or complement operation. Okay, this is F10. Now we are going to see for F11 function. So for F11 function what we are getting is we are getting 0 output for only one input, that is 0 1, but for 0 output we go for the max terms instead of the min terms. So the final expression that we are writing for this F11 function would be X plus Y bar. Okay, this is known as implication gate. Okay, this is known as implication gate. Now we are going for F12. So what is F12? So the F12 function is the output for F12 function is 1100 and X input is 0011. So these are complement to each other. So we can write F12 is X bar, that is complement operation. So this is a complement operation. So up to F0 to F12 we have understood. Now we are going to see F13, F14 and F15. So for F13 we can see the output would be for F13 the output is 0 for only one input, that is 10. So we are writing the expression in a form of max term. So it would be X bar plus Y, which is also an implication gate. Okay, this is also an implication gate. Now we are going to see for F14. So for F14 we can see that F1 and F14 are complement to each other, because for F1 it is 0001 and for F14 it is 1110. So we can know that as F1 is the AND operation, so the F14 would be our NAND operation, that is X dot Y bar, and it would be our NAND gate. Okay, now we are going to discuss about F15. So what would be F15? So the output for F15 is 1111. That is for all the input combinations the output is 1. So it is known as the identity gate. So F15 is 1, which is known as our identity gate. Okay, so in this table we are able to understand what are the different distinct possible Boolean expressions or the functions for two input system. Similarly, if we are going for 3 input system and the 4 input system, we are also able to understand what are the distinct Boolean functions possible for that input system. So here we can see that from F0 to F15 all the functions are distinct in nature, and this is the total amount of distinct Boolean functions that are possible for a 2 input system. Okay, now we move on to our Boolean algebraic laws. So what are Boolean algebraic laws? First law is commutative law. So I am writing its final expression. You can solve or you can prove it by a truth table. So in the GATE exam it is not necessary to get the proof. So I am writing the final expression, because the most important thing is to learn the final expression, because it is sometimes used in the simplification process. So the commutative laws is A plus B is equals to B plus A, or A dot B is equals to B dot A. Okay, this is our commutative law. Now we are going for associative law. So what would be the associative law? A plus within bracket B plus C would be equals to A plus B within the bracket plus C. Or we can write for dot product also. So it would be A dot B dot C in a bracket, which is equals to A dot B within a bracket dot C. So these are commutative and associative law. Now we are going to write for distributive law. So what is a distributive law? It would be A dot B plus C would be equals to AB plus AC. This is known as distributive law. Or we can write this as in a different method, that is A plus B dot C plus D is equals to, just open the brackets, AC plus AD plus BC plus BD. So this is our commutative law, associative law, as well as the distributive law. Now we are looking for the AND operation theorem. So in the previous lecture already we have learned so much about the AND operation. So just write the formulas to make the notes properly. So what are the formulas? A dot A is equals to A, and A dot 0 would equals to 0, Okay, and a dot 1 would be equals to again a, and a dot a bar would be equals to 0. So this is our AND operation theorem. Now we are going for involution theorem. So what is involution theorem? It would be a bar with another bar is equals to a only. So taking complement 2 times would result in a same function. Okay, this is our involution theorem. Now we are going to see for OR operation theorem. So what is OR operation theorem? All the methods that we have learned, all the expressions that we have learned in OR operation, we are just summarizing here. So for OR operation, a plus a is equals to a plus 1 would be equals to 1, because it would not depend on a. The answer would always be 1, because 0 plus 1 is 1 and 1 plus 1 is also 1. And a plus 0 would be equals to a, and a plus a bar would be equals to 1. So this is commutative law, associative law, distributive law, AND operation law, involution theorem, as well as the OR operation theorem. So you can write these points, then we are moving towards our rest of the algebraic laws. So the next theorem that we are discussing is De Morgan's theorem. We already know what is De Morgan's theorem. Just to write the points we are writing. So what is De Morgan's theorem? We know that it would be x plus y whole bar would be equals to x bar dot y bar, or we can write x dot y bar would be equals to x bar plus y bar. Okay, this is our De Morgan's theorem. Now we are writing for transposition theorem. So what is transposition theorem? Transposition theorem means operations or the associations can be interchanged. So what it means, we are writing through the Boolean expression. If it is a dot b plus a bar dot c, so we can interchange the operators as well as the associations. So we can associate these two and these two. Okay, so how we are going to write? A dot b plus a bar dot c would be equals to a plus c dot a bar plus b. Okay, this is our transposition theorem. Now we are going to see what is absorption theorem. So absorption theorem states that x plus x dot y would be equals to y, because what it means, it will be equals to x, because when we take x plus xy, we take common x, that would be 1 plus y, so it would be x. So output would be x, and we can write one more theorem with respect to the same. It would be x plus x bar y would be equals to x plus y. What it means, that if it is x plus x bar dot y, by using the theorem we can write it is equals to x plus x bar dot x plus y, so it would be equals to x plus y. So this is our absorption theorem. Okay, so you can write these theorems. Then we are going to discuss about the distribution theorem. So distribution theorem states that a plus b dot a plus c is equals to a plus bc, or we can write in xyz form also. X plus y dot x plus z is equals to x plus y z. Okay, so this is our distribution theorem. The last theorem that we are going to discuss is consensus theorem. What it states that it represents, or it is used in to find the redundant group. Okay, redundant group. So what it states that if a variable is associated with the another variable, so if it is a dot b, and if its complement, if the complement of the first variable is associated with the another variable, so the third term that is constructed by the rest of the variables is our redundant group. Okay, this is our redundant group. So what it means to be redundant group? It means that there would be no effect in the result with the presence or the absence of this group. So how we are going to construct, or how we are going to find the redundant group? The method is very simple. So if there is a variable a, we are taking an example. So if there is a variable a and it is associated with another variable b, and its complement is associated with another variable c, so the association of the rest of the two variables, that is b and c, would be our redundant group. So how we are going to prove this? So you can prove it very simply. It is a dot b plus a bar dot c plus a plus a bar bc. Okay, so this was now expanding a dot b, because a plus a bar is equals to 1, so we can write it like this. So it is a dot b plus a bar dot c plus abc plus a bar bc. Okay, now taking ab common from ab plus abc, it would result in ab 1 plus c, and taking a bar c from these two terms, the rest of term would be 1 plus b. So it would become 1, this would also become 1, so the final answer would be ab plus a bar c. So this is the way to find the redundant group. What redundant group means is that there would be no effect, there would be no effect with the presence or absence of this group. Okay, so this was our consensus theorem, and this gives the base of the redundant group. Okay, so these were the theorems. Now we are going to solve one example related to all the theorems, or general example. We have been given that there is a function a comma b which is equals to a bar plus b. So we have to find the answer or the value for f function x plus y comma z. So how we are going to solve? First we are going to solve the inner function, which is f x plus y comma y. So it would be x plus y bar plus y. Okay, so by applying De Morgan's theorem, we will write this x bar dot y bar plus y. Okay, so we can write using the theorem it is equals to x bar plus y. Okay, because by taking let me expand or do it completely. It would be x bar plus y dot y plus y bar. So it would become 1. So the final expression would be x bar plus y. Okay, so this was the inner function. Now it would be x bar plus y comma z. Okay, so by using this as a base, so it would be x bar plus y whole bar plus z. So it would be x bar dot y bar plus z. So the final answer would be x dot y bar plus z. Okay, this is our final expression. So I hope you are able to understand how we are going to solve these kind of problems. Now we move to the positive and negative logic. So what you mean by positive logic and negative logic? Normally in our basic digital electronics, we only consider the positive logic. So what is positive logic? In the positive logic, we take high input as logic 1 and low input as logic 0, because all the in the normal application we take plus 5 volt as logic 1 and 0 volts as logic 0. Okay, so normally we use positive logic, but there also a negative logic, which is high input is equals to logic 0 and low input is equals to logic 1. So let us try to more understand what is positive and negative logic. You can construct this table also. So let us consider one example. We are drawing a truth table, that is with the two inputs AB. This is 0 0 0 1 1 0 1 1, and let the function be an AND operation. Okay, this is an AND operation. So it would be 0 0 0 1. So this is our positive AND. We are taking that it is a positive AND, which means 0 logic is equals to 0 input or the low input, and logic 1 is equals to the high input. So this is our positive AND. So if we want to convert our positive AND or the positive logic into negative logic, we are just interchanging the logics. That is, in the place of 0 we are writing 1 and in place of 1 we are writing 0, because here we can see that to convert a positive logic into a negative logic, we just want to replace 1 with 0 and 0 with 1. So the AB inputs are like this, and this is our function. Okay, so the output would be 1 1 1 1 0 1 0 1 1 and 0 0 0. Okay, so if just keep in mind, just remember or just look this table only. Okay, just look only on this table. What this table resembles to, you can see it resembles to positive OR. Okay, this is a positive logic of OR operation. Okay, because for 1 1 input output is 1, for 1 0 output is 1, for 0 1 output is 1, and for 0 0 output is 0. But because of we interchange the positive logic in the negative logic, this expression also is equals to the negative negative logic of AND operation, which is equals to our positive OR. Okay, so we have proved this note, students, that a negative AND is equals to a positive OR. Similarly, a negative NAND is equals to a positive NOR. So how to convert a positive into a negative logic or vice versa? We use the concept that is duality. So there is one point also, thus dual is used to convert a positive to negative logic and vice versa. So if we want to convert a positive logic into a negative logic, we are using the duality principle. So to understand the duality principle, first we have understood what is the difference between the positive logic and the negative logic. So now duality is simple. We know what we are doing. It is equivalent to write the negative logic of a given Boolean expression. So what are the steps involved to convert a positive logic into a negative logic, or what is the method to find the dual of any expression. So the first step is to interchange the operator, that is dot to plus, or if it is plus, so it can be converted into dot, and interchange the identity, that is 0 to 1 and 1 to 0. One point to remember, students, is that there is no change in the variable. So this is the difference between the duality as in the complement. In the next slide we are going to see what is the complement, but remember, in duality there is no change in the variable. So let us consider one example. We are taking a function which is f is equals to x plus y bar plus z. So if we want to know its dual, what is its dual form, so we are just changing the operator, that is plus to dot, so it would be x dot y bar dot z. So this is our dual form. Okay, this is our dual form. This is the way to convert or to get some any expressions dual form. So this is example 1. Now take another example, which is f function equals to x plus y bar dot z. So what would be its dual form, students? Just change the operator, x dot y bar plus z. So this is the way to get the dual expression for any Boolean function. Okay, so you can write this point. It is equivalent to the negative logic of a given Boolean expression. Finding a dual, or what are the steps involved? These steps are important. So the step 1 is to interchange the operator, and the step 2 is to interchange the identity. So another note which is very important, there is no change. We can mark a star on it. There is no change in the variable. So these are the two examples. Now there is some other notes also. So the first note is, if a dual of an expression results in the expression itself, then it is known as the self-dual. Okay, so it is known as self-dual expression. For n variables, the maximum possible self-dual expressions is 2 raised to power n minus 1. So how we are going to prove? Let us take n equals to 2 inputs. Okay, so write these point, and let in the next sentence write as an example, we are taking n equals to 2 inputs. So number of self-dual expressions would be, self-dual expressions would be 2 raised to power 1. That would be 4 self-dual expressions. Okay, what do you mean by self-dual expressions? If the dual of the expression results in the expression itself, then it is known as a self-dual expression. So how we are going to prove it? So in the first slide, when we constructed all the possible functions of a 2-input system, we are going to see what are the self-dual expressions in that. So the first expression for the self-dual expression is f3, because if we take its self-dual, or if we take its dual, the result would be x only. So it is our first expression. The second expression is y, because if we are taking its dual, it would remain the same. The third expression is y bar, because there would be no change in the variable, so it would remain y bar only. And the fourth expression would be x bar. So by taking the dual of x bar, it would remain x bar only. So these are the 4 possible expressions. Some students are confused why f0 and f15 are not the self-dual expressions, because students, in the step 2 we have written interchange the identity also. So what in the interchanging the identity, we are converting 0 to 1 and 1 to 0. So if we take the dual of this expression, it would be equals to 1, which is not equals to is to its expression, original expression. So this is not a self-dual expression. Okay. So these were our self-dual expressions for a 2-input system. Okay. So this note is proved. Now the third note is, with n variables, maximum possible distinct logic expressions we have already studied. It is equals to 2 raised to power 2 raised to power n. So quickly write these 3 points. Then we are moving towards the complementary theorem. What is the complementary theorem? Yes students, there is one point also which is very important to remember while discussing the degenerative forms. While constructing a degenerative forms, while learning the degenerative forms, we have made a table for a non-degenerative expressions. Okay, degenerative expression. Okay, so what were the non-degenerative forms or the expression? We have made a table which is AND, NAND, NOR, OR. Okay, then AND, NAND, NOR, OR. Now AND, NAND, NOR, OR, and NAND, NOR, and this is OR. So these were the 8 non-degenerative forms. But if we want to look the row wise, we have already discussed in that table also, but now we are discussing the dual form, so it would be better to understand here only. So if we look row wise, these AND OR forms is equals to the dual form of OR AND. So if we want to take the dual of AND OR form, it would result in OR AND form. Similarly, if we take the dual of NAND NAND, it would result in NOR NOR. Similarly, for NOR OR, it would be NAND AND, and for OR NAND, it would be AND NOR. So to prove one point, we are taking the example for AND NOR form. So AND OR form would be like this if it is x dot y plus z. So it is a AND OR form. So if we want to make it dual, we are just changing the operator. That would result in x plus y dot z. So it is resulted into an OR AND form. This was AND OR form, and this resulted into a OR AND form. So we can see by looking row wise, we are getting the dual forms of each other. So you can make this table also. This would be this table is useful for two methods. First is to know what is the non-degenerative forms, and second is for the dual forms. So you can write these 3 points, you can construct this table, then we are moving towards our complementary theorem. Okay. So now we are going to see what is complementary theorem. So the first step to find someone's complement, or if we want to find the complement of some expression, what is the first step? First step is to take its dual form. Okay, and the second step is to complement the individual variable. By doing these two steps, we are able to find the complement of any expression or the function. So just take one example. If the function is x bar dot y plus z, okay, so if we want its complement, first step is to find its dual form. So what would be its dual form, students? It would be x bar, there would be no change in variable, plus y, there would be change in operator, dot z. Okay, this is its dual form. So now second step is to complement each variable. So we can get its complement, or we can write it fc or f bar would be equals to x bar dot, sorry, we have to complement the each individual variable, so it would be x plus y bar dot z bar. So this is our answer for its complement. So these are complement to each other. So this is the complementary theorem. So quickly write this point, then we are moving towards next slide. Now the next point is canonical and standard form. So first we are going to see what is canonical form, and next we are going to see what is standard form. So in canonical form, all the terms contain each literal. Okay, so what it means, let us understand with an example. If we are taking a function which contains three literals, that is a, b, c, and the function is somewhat like this, a, b, c plus a b bar c plus a bar b c plus a b bar c bar. So the function is having four minterms. Okay, and each term, we can see in each term there are all the three literals present, that is a, b, c. So this is known as the canonical form. But if we are going for the standard form, it means that all the terms doesn't contain each literal. So if we take the example, function a comma b comma c, these are the three literals for the function, and it would be like somewhat like this, a plus bc plus a bar b bar c. So if we are considering only three terms, we can see that in each and every term there are no three literal, all the three literals present, because in this b and c are not present, in this term a is not present or a bar is not present, and in this all the three is present. So this is known as the standard form, and this is known as canonical form. So this is the difference between the standard and the canonical form. Okay students, now we are moving towards the reduction techniques. So what are the reduction techniques? So to understand what are the reduction techniques, first we are going to see what are SOP form and what is POS form. So SOP form stands for sum of products form. Okay, this is known as sum of products form. So what you mean by sum of product forms? If we take a truth table that is having two inputs, 0, x and y, so let us take it is 0 0 0 1 1 0 1 1. So in SOP form, x is taken as 1 and x bar is taken as logic 0. Okay, so if it is xy, so its decimal equivalent would be 0 1 2 and 3. Okay, so the possible number of minterms, that is, what would be the minterms for this two input combination? It would be x bar dot y bar. Okay, it would the next term would be x bar dot y the third would be x dot y bar, and the fourth would be x dot y. So this is the minterms and this is the two inputs x and y. Now we consider as an example a function which is like 0 1 0 1. So what would be its SOP form? So SOP form is equals to sum of products. So it would be sum of the minterms, that is the function for which the output for which the function for which the output is 1 1, we are taking those terms, and it would be equals to x bar dot y plus x dot y. This is our function. We can write it in another way like sigma, that is sum of the minterms, that is the function is 1 for 1 and 3. So this is the another form to write the SOP structure. Okay, so this was SOP form. But if we want to make a POS form, so what is a POS form? POS form stands for product of sum form. So in product of sum form, we are taking again an example with two inputs. In product of sum form, of sum form, x or the normal form is equals to 0 and x bar is equals to 1. Okay, so if it is x, y, two inputs and it is 0 0 0 1 1 0 1 1, so its decimal equivalent we can write, so this would be so the maxterms, the decimal equivalent would be 0 1 2 3, and the maxterms would be are like this. It would be x plus y, and this would be x plus y, this would be x plus y bar, this would be x bar plus y, and this would be x bar plus y bar. So we can see maxterms are the x plus y bar, x bar plus y, and x bar plus y bar. So if we consider one function that is similar to above, which is 0 1 0 1, here we see the zeros, so the function would be equal to x plus y dot x bar plus y, which is equals to the product of max terms 0 comma 2. Okay, because the decimal equivalent for the output 0 0 is 0 and 2. So if we simplify this function, it would be x dot x bar, x dot y, x bar dot y plus y dot y. So it would be this term would become 0, and this would be y plus x dot y plus x bar dot y. So it would be y, because when we take common y 1 plus x bar, so the answer would be y. And if we simplify this expression also, we are going to see if we take common y, so it would be x plus x bar, so it would again become y. So we can see that sigma of minterms 1 comma 3 is equals to the product of maxterms 0 comma 2. This is a very important expression related to the SOP and POS form. So if what the terms which are included in the min terms, the rest of the terms would be our max terms. So sigma of min terms 1 comma 3 is equals to the product of max terms 0 comma 2. So this is a very important note. You can write this note, and you can write these two forms also, that is SOP form and POS form. Okay. Now quickly write these points, then we are moving towards our next point. So the next point is Kmap. Kmap stands for Karnaugh map. Okay, this is Karnaugh map, and it helps in reducing the Boolean expression or logic minimization. So it can be possible for 2 variables, 3 variables, for any number of variables. Okay, so normally we are faced with 3 types of variables, that is 2 variables, 3 variable Kmap, and 4 variable Kmap. So let us construct a 2 variable Kmap. If it would contain 4 cells representing all the minterms and maxterms, if this is A and this is B, so it would be A bar A and B bar B. It would be 0, 1, 2, 3. So each cell represent one minterm. Okay, this is a 2 variable Kmap. Now we are drawing for a 3 variable Kmap. So let us draw a 3 variable Kmap. It would contain 8 cells representing all the minterms. If it is A and this is BC, so it would be A bar and A. It would be B bar, C bar, B bar, C, BC and BC bar. So this would be, if we are taking A as a MSB, most significant bit, so it would be, the minterms would be 0, 1, 2, 3, 4, 5, 6, 7. We already know about the Kmap, but just we are revising some of the concepts related to it. So if we are taking MSB on this column, we are going to write 0, 1, 2, 3, 4, 5, 6, 7. Why we are writing like this? Because in the Kmap there would be only one variable change. Okay, and if we are taking LSB in the column, what would be our Kmap? If we are taking C and this is AB and this is our LSB, that is least significant bit, it would be C bar C, it would be A bar, B bar, A bar B, AB and AB bar. So it would be 0, 1, 2, 3, 4, 5 and 6, 7. These are the possible ways of the minterms. Okay, now we are discussing for 4 variable Kmap. So for 4 variable Kmap, there are 16 cells representing all the minterms. So if this is AB and this is CD, so it would be A bar B bar, A bar B, AB and AB bar, and this would be C bar D bar, C bar D, CD and CD bar. So minterms would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So these are the possible minterms for a 4 variable Kmap. What is the method to solve the Kmap? For if we are giving a SOP form or the sum of product terms, then we are putting the 1 in these cells for all the minterms, and we try to construct a group so that the output can be simplified. So if we are going for 4 variable Kmap, so what are the possibilities of forming the group? It can be a pair of 2 cells. Okay, so it can be a pair, it can be a quad, which is a combination of 4 cells or the 4 minterms or maxterms. It can be a octet of 8 minterms or 8 maxterms, or it can be a complete whole Kmap. Okay, so these 3 are most important: pair, quad and octet. So the first point that is note regarding the Kmap is always form the larger group first and then find the redundant group. So when we are going to study about the redundant group, we are going to see this point. So just write this note in this place and construct all the Kmap for all the variables, that is 2 variable, 3 variable and the 4 variable. Okay. So now we are going to see some of the examples related to the Kmap. We have been given the sum of product form. This is the SOP form, and these are the minterms possible for a 4 variables. So let us construct a 4 variable Kmap. So while constructing the Kmap, students, we should understand why we are solving through Kmap. Because if we just use the logic minimization by using all the various algebraic laws, it would takes a huge amount of time. So to reduce our time and the efforts, we are using the Kmap. Okay, so if this is our Kmap, 4 variable Kmap, it would be a bar, b bar, a bar, b, ab and ab bar. This would be c bar, d bar, c bar, d, cd and cd bar. So what would be minterm? 0, 1, 2, 3, 4, 5, 6, 7 and this would be 8, 9, 10. This would be 8, 9, 10, 11. This would be 12, 13, 14 and 15. Okay, so let us mark the minterms. So minterms would be 0, 1, 2, 4, 5, 6, 8, 9 and then 12, 13, 14. Okay, so first go for the largest group. So we are not able to form the whole group, we are able to form one octet. So this is our octet formation. Okay, so this is one octet. So the expression for the octet would be C bar. Okay, now we are able to form two quads. This is one quad and second is this quad. This is 2 quadrants. So the expression for these 2 quadrants would be in these 2 terms the common is a bar, so we would write a bar, and in these 2 terms the common is d bar, so we would write d bar. Similarly, in these 2 terms, if we want to write the minimized expression for this quad, we would take the common terms, that is b, and in these 2 terms the common is d bar. So this is c bar plus a bar d bar plus b dot d bar. So this is our final expression. So this is our final expression. So the most important point regarding the Kmap is when we get its final output, it can't be reduced more. So this is a final reduced or the simplified form of this function. Now it can't be reduced more to the less number of terms. This is our final expression. Similarly, now we are going to see our next example, but before that we are going to see some of what is don't care conditions. So students, what is don't care conditions? Let us consider an example. So if we are considering one example, like just understand what is don't care conditions. There is no need to write these points. So if we are taking one example, like if we are constructing a alarm clock and we are using the digital format, and we want a alarm to be ring at 5 a.m. and 6 a.m. Okay, so what are the possible combinations? So the clock would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So these are the possible ways. But to construct 1 to 12 we need 4 variables, and by using 4 variables the number of minterms possible are from 0 to 15. So if we if we are forming a clock, there would be no 0, there would be no 13, there would be no 14, and there would be no 15. So 0, 13, 14 and 15 are the don't care conditions in this formation or in this function. So what are the don't care conditions, students? Like if we are making a clock, the example that we have studied, the 0, 13, 14 and 15 are the don't care conditions. If we are just utilizing them to minimize our expression. So one point regarding the don't care condition is that if we are writing a note here. First note is, if we are able to construct a larger group using don't care conditions. In don't care conditions, the value can be either 0 and 1. So we are not very much involved or taking care of these conditions. We are just representing with a cross sign. So if we are able to construct a larger group using don't care conditions, then only we will include them. What it means that if we are able to construct a larger group in a Kmap using the don't care conditions, then we are only going to include them unless we are not including them in our Kmap. Okay, so if we are taking an example using this, we have an example of a function ABCD with minterms 1, 3, 7, 11 and 15. And these are the don't care conditions, that is 0, 2 and 5. So for 0, 2 and 5, the output can be either 0 or it can be 1. So there is no fixed 0, 1. So just we are representing it with a cross sign. Okay. So there is no surety whether it would be 0 and 1. So we are just representing it with 0 sign. The minterms are 0, 1, 2, 3, 4, 5, 6, 7. This would be 8, 9, 10, 11 and 12, 13, 14 and 15. So the minterms given are 1, 3, 7, 11 and 15, and the don't care conditions are 0, 2 and 5. So now we would like to go for the largest group in the Kmap. So the largest group possible are quadrant, because there is no formation of octet or the complete group. So first quadrant can be this. So this is our first quadrant. Now the second quadrant can be this quadrant, in which there are 3 minterms and 1 don't care condition, or either it can be 2 don't care conditions and 2 ones. But we take that quadrant in which there are minimum number of don't care conditions. So for this example, the second quadrant would be this quadrant in which there are 3 minterms and only 1 don't care condition. Okay, these two don't care conditions are not involved in final solution. So this is the way to form the Kmap. Now there are some more points regarding the redundant group, implicants, and one more point. So that would we will study in the next lecture, and in the next lecture we are going to see some problems on the Boolean algebra also. So the next lecture would be the problem sessions and the rest of the topics in which we are going to see are the redundant groups, what are redundant groups, and what are the prime implicants, and what are the way to construct any logical expression using two input NAND and NOR gate. So thank you for this lecture.